Section: Introduction. We're going to talk about how we can improve the way large language models, LLMs, understand and generate language. These models have made significant progress in this area, but their success often depends on how well they align with human preferences. This alignment is usually achieved through a process called reinforcement learning from human feedback, RLHF. In RLHF, we typically start by creating a reward model based on human preferences. This model assigns a score to each output of the language model, similar to how chess players are ranked based on their relative strengths. We then refine the model by optimizing its performance using reinforcement learning. However, this approach has its limitations. For instance, there are situations where maximizing the score doesn't necessarily align with maximizing the probability of winning against other players. To address these limitations, we propose a new approach called Nash learning from human feedback, NLHF. Instead of focusing on a reward model, we concentrate on learning a preference model. This model takes two responses as input and produces a preference score, indicating which response is preferred given a certain context. We can initialize this preference model using an LLM, and then refine it using supervised learning to align it with human preference data. Unlike the traditional RLHF approach, a preference model doesn't depend on the distribution of responses used to collect human data. It remains essentially the same regardless of the policy used to generate these responses. We believe that the Nash equilibrium of the preference model, a solution that aligns with the diversity of human preferences, is a better measure than the maximum of the expected reward model. Once we have the preference model, our main goal is to calculate the corresponding Nash equilibrium. This equilibrium represents a policy that consistently produces preferred responses over responses generated by any other policy. We believe this approach is more aligned with human preference data. To approximate the Nash equilibrium, we use a deep reinforcement learning algorithm. We generate two responses, one under the current policy we're optimizing, and the other under an alternative policy. We then compute the preference score, and use this as a reward for optimizing our policy. In this work, we introduce the concept of NLHF and define a regularized variant of the preference model. We also establish the existence and uniqueness of the Nash equilibrium in this context. We then introduce a novel algorithm named Nash-MD, which converges to the Nash equilibrium and learns by competing against alternative policies. We also introduce Nash-EMMA, a variation that uses an exponential moving average of past policy parameters. We present the results of extensive numerical experiments conducted on a text summarizing task. In these experiments, we train several models using the NLHF approach and evaluate their performance. We conclude that NLHF offers promising new ways to align LLMs with human preferences. Section Summary. Large language models, LLMs, have made significant progress in natural language understanding and generation, particularly in conversational applications. However, the prevailing approach of reinforcement learning from human feedback, RLHF, using the ELO model has limitations in accommodating diverse human preferences. In this paper, we propose Nash learning from human feedback, NLHF, which focuses on learning a preference model and computing the Nash equilibrium to better align with human preferences. We introduce two algorithms, Nash-MD and Nash-EMMA, for approximating the Nash equilibrium and demonstrate their effectiveness in training LLMs on a text summarization task. Section: Prior work. Our work is part of a larger field known as preference-based reinforcement learning, RL, where we learn from human preferences rather than a pre-designed or learned reward. This approach was first proposed and popularized by previous researchers, who suggested learning a reward model from preference feedback and then optimizing the policy against this model. However, we believe that directly optimizing for preferences can help avoid reward hacking, where agents maximize a reward without performing the intended task. This is particularly useful in areas like healthcare, where providing a single reward might be challenging or even undesirable. In our work, we focus on trajectory feedback, where experts provide feedback by choosing the preferred trajectory from two options. This simple form of feedback is easy to implement and has been used in various applications like summarization, question answering, and language-based assistance. More complex forms of feedback have been explored in theoretical literature. We now move on to the main concepts behind our approach to learning from preference feedback. We consider a preference model in a contextual bandit setting. Here, given a context, x, and two actions, y, and y prime, the preference of y over y prime is a number between 0 and 1, denoted as p, y over y prime given x. We assume this preference model is symmetric, meaning the preference of y over y prime is the opposite of the preference of y prime over y. An example of such a preference model could be the probability that a scoring function f for y is greater than or equal to f for y prime under some random outcome, z. This could represent the probability that a randomly chosen human prefers choice y over y prime in a given context, x. We assume that we only have access to their relative preferences, not the absolute human scores, f. We also define the preference between two distributions conditioned on a state x and the preference of an action over a distribution. Furthermore, given a distribution, rho, over contexts, we define the preference between two policies. A policy, pi, is preferred over another policy, pi prime, if the preference of pi over pi prime is greater than or equal to 1/2. In this paper, our goal is to find a policy, pi star, that is preferred over any other policy. This goal defines a two-player game, where the players select policies, pi and pi prime, and the first player receives a payoff of the preference of pi over pi prime, and the second player receives the opposite. This is a two-player, symmetric, constant sum game, and when both players use a policy, pi star, that solves this equation, it results in a Nash equilibrium for this game. Our approach differs from most existing work on RLHF in two main ways. First, our objective is expressed directly in terms of preferences, not in terms of a reward function learned from preferences or a nonlinear transformation of the preferences. Second, our solution relies on the concept of Nash equilibrium, rather than optimization against a fixed behavior. We will discuss the impact of these choices through several examples in the following sections. Section Summary. In the field of preference-based reinforcement learning, RL, our contribution focuses on learning from pairwise human preferences instead of using scalar rewards. By directly optimizing for preferences, we can avoid reward hacking and accommodate domains where a single scalar reward may not be suitable. We specifically focus on trajectory feedback, where experts select their preferred trajectory from two proposed options. Our approach involves a preference model in a contextual bandit setting, where we aim to find a policy that is preferred over any other alternative policy, resulting in a Nash equilibrium. This differs from existing RLHF work as it directly uses preferences and relies on Nash equilibrium rather than optimizing against a fixed behavior. Section. Limited expressivity of reward models. Let's discuss the limitations of reward models. Generally, a preference model might not always follow a logical order. For instance, we could have three strategies. Let's call them Strategy 1, Strategy 2, and Strategy 3. It's possible that Strategy 1 is preferred over Strategy 2 more than half the time, Strategy 2 is preferred over Strategy 3 more than half the time, and yet, Strategy 3 is preferred over Strategy 1 more than half the time. To illustrate this, let's imagine a set of outcomes represented by the numbers 1 through 9. We define three strategies. Strategy 1 chooses from the numbers 2, 4, and 9. Strategy 2 chooses from the numbers 1, 6, and 8. And Strategy 3 chooses from the numbers 3, 5, and 7. Each strategy picks a number from its set randomly with equal probability. We then define preference as the likelihood that the number chosen by one strategy is greater than the number chosen by another. In this case, each of the three preferences, Strategy 1 over Strategy 2, Strategy 2 over Strategy 3, and Strategy 3 over Strategy 1, occurs 5 out of 9 times. This is similar to the classic example of non-transitive dice. This example shows that preference models can handle non-transitive preferences, something that reward models, which assign a single score to each strategy, can't do. The question of whether humans exhibit non-transitive preferences has been a topic of research for a long time. Moreover, non-transitivity isn't the only limitation of reward models. For instance, there are cases where the ELO score, a type of reward model, fails to accurately rank strategies, even when the preferences are transitive. We argue that preference models provide a more flexible and nuanced way to model human preferences than reward models. Now, let's consider a modified version of the preference model that includes a penalty mechanism. This is useful in situations where the preference model is more accurate when following a certain strategy. This could be the strategy that was used to generate the training data for the preference model, or in cases where it's important to stay close to a known safe strategy. In these cases, we use a method called KL regularization to measure the difference between the strategy being considered and a reference strategy. The regularized preference between two actions is defined as the preference for one action over the other, adjusted by a penalty term that depends on the difference between the probabilities of the two actions under the strategy and the reference strategy. Similarly, we define the regularized preference between two strategies. We can show that there is a unique optimal strategy for this regularized preference model. This is because the preference for one strategy over another is a linear function of the strategies, so the regularized preference is a concave function of the strategy and a convex function of the other strategy. The existence of an optimal strategy follows from a mathematical result called the minimax theorem, and its uniqueness comes from the fact that the function is strictly concave or convex. Finally, let's discuss how to find the optimal strategy for the regularized preference model. This model defines a two-player game where one player chooses a strategy and the other player chooses another strategy. There are well-known methods for finding the optimal strategies in such games. Some methods guarantee that the average of the strategies chosen over time converges to the optimal strategies, while other methods guarantee that the last strategy chosen converges to the optimal strategies. Section Summary. Preference models have the ability to capture non-transitive preferences, which is not possible with reward models that assign a single score to each policy. Regularized preference models incorporate a penalty mechanism, such as KL regularization, to quantify the divergence between the policy under consideration and a reference policy. The regularized preference model has a unique Nash equilibrium, and there are algorithms available to approximate this equilibrium. Section. Convergence on average. Let's break down the complex concepts in the given text and simplify them for better understanding. The text discusses a strategy known as fictitious play, FP. In this strategy, each player, at every turn, chooses their best response against a blend of the opponent's past strategies. This blend is referred to as the mixture policy. The text states that this mixture policy tends to converge to a state known as the Nash equilibrium in constant sum games. The Nash equilibrium is a state of a game where no player can benefit by changing their strategy while the other players keep theirs unchanged. The text also mentions the use of online convex optimization in the context of solving convex-concave constant sum games. Here, each player aims to minimize their own convex loss. The concept of regret minimization is also discussed. It's a strategy where the average strategy of self-playing no-regret algorithms converges to a Nash equilibrium. The text then talks about different techniques that provide faster rates of convergence. These techniques have been studied in both discrete and continuous time settings. The text also discusses the convergence of the last iterate. It mentions methods like extragradient or optimistic mirror descent that have been proven to converge to a Nash equilibrium. The text also mentions the optimistic multiplicative weights update method, which provides convergence guarantees to the Nash equilibrium of the last iterate. The text then introduces a new algorithm called Nash-MD, a variant of mirror descent. This algorithm uses a specific regularized policy, which is a geometric mixture between the current policy and the reference policy. The text states that this algorithm improves the current policy in a direction that increases the preference against the regularized policy, while not deviating too much from it. The text concludes by stating that the Nash-MD algorithm does not require playing against the full mixture. Instead, it plays against a single geometric mixture between the current policy and the reference policy. This is particularly important in situations where storing and generating samples from several policies is costly. Section Summary. The section discusses the convergence properties of the Nash-MD algorithm, which is a variant of mirror descent. The algorithm uses a regularized policy that is a geometric mixture of the current policy and a reference policy. The main theoretical result shows that the algorithm achieves last iterate convergence to the regularized Nash equilibrium at a speed of approximately 0.1 t, where t is the number of iterations. Importantly, the algorithm does not require playing against the full mixture of past policies, making it computationally efficient in situations where storing and generating samples from multiple policies is costly, such as in LLMs. Section. Nash-MD has a last iterate convergence property. The Nash-MD algorithm has two key properties. Firstly, it has a last iterate convergence property. This means that the current policy, which we'll call pi_t, converges to a final policy, pi_tau asterisk. This is different from other algorithms like fictitious play and regret minimization algorithms, which typically only converge on average. This feature is especially important in the context of language learning models, LLMs, because it saves substantial memory resources that would otherwise be needed to store a mixed policy, which we'll call bar pi_t. Let's compare Nash MD with another algorithm called online mirror descent, OMD. In general, we can analyze constant sum concave convex games using online convex optimization. The goal here is to find a sequence of solutions, pi_t, that minimizes the sum of a sequence of convex loss functions, L_t, pi. The OMD algorithm defines a sequence for which the average cumulative regret can be bounded as 1t times the sum from t equals 1 to t of L_t, pi_t, min_pi 1t times the sum from t equals 1 to t of L_t, pi, which is approximately proportional to 1 sqrt, t. This upper bound on the regret can be used to deduce a convergence result in constant sum games where each player would play an OMD strategy to minimize their own convex loss. In our context, we could apply this OMD strategy to minimize the regularized preference model, p_tau. Since p_tau is symmetric, we only need to consider the dynamics of a single player. So, the loss function at time, t, is the negative preference against the current policy of the opponent, L_t, pi, equals p_tau, pi follows pi_t. We can rewrite the OMD update rule using the regularized policy, pi_t_mu. Comparing this with the Nash MD algorithm, we see that both use the same KL penalty term, KL, pi_t_mu. However, they differ in that OMD optimizes the preference against the current policy, pi_t, whereas Nash MD optimizes the preference against the regularized policy, pi_t_mu. In the context of convex-concave games, the regret bound on the average cumulative regret translates into an upper bound on the exploitability of the game when players play their average policies, leading to their on-average convergence to the Nash equilibrium. However, it's known that usual regret minimization algorithms may not have a last iterate convergence property because the sequence of policies, pi_t, may oscillate around the Nash equilibrium. Despite this, last iterate convergence has been achieved for variants of OMD, such as extra gradient and optimistic versions. To our knowledge, Nash MD has not been introduced before, despite its simplicity. Nash MD has a last iterate convergence property with a KL divergence to the Nash equilibrium decaying as (1t). We believe this simple modification of OMD has these properties because of the special structure of the regularized preference function that we consider here, which is the sum of a bilinear function, in policy spaces, and a KL penalty term. All the results mentioned in this section are for the state-independent case, where policies and preferences do not depend on the context, X. In the case of LLMs, the context is the prompt, X, and responses, Y, and Y, are generated conditioned on X. However, the theoretical results do not change. We define the Nash MD algorithm in the contextual bandit case as follows. For every X, in the support of rho, pi_t plus 1, CDOT, X, is defined as the argument that maximizes the expression involving pi_t_mu, Y, X. We prove the convergence of this algorithm in the same way as in theorem, by showing that at every iteration, t, we have a certain inequality involving the KL divergence. Section summary. The Nash MD algorithm has a last iterate convergence property, meaning that the current policy converges to the optimal policy, rather than just converging on average like other algorithms. This is particularly important in the context of large language models, LLMs, due to the memory resources required to store a mixture policy. The algorithm is similar to online mirror descent, OMD, but with a different optimization objective that leads to convergence to the Nash equilibrium. Additionally, the algorithm can be extended to the contextual bandit setting without changing the theoretical results. Section. Implementation of NLHF. Let's delve into the implementation of NLHF, using insights from Nash MD. We're going to look at how we can use gradient-based algorithms in deep learning structures to calculate the Nash equilibrium of a preference model. We're particularly interested in how this applies to language learning models, LLMs. In LLMs, tokens are usually generated one at a time, rather than in a full sequence. This is done in an autoregressive manner, meaning that the generation of each token depends on the ones that came before it. So, if we have a response, let's call it y, it can be represented as a sequence of tokens from y0 to yn. Each token, say yn, is generated from a distribution that is conditioned on the previous tokens. In our experiments, we implement this token-by-token generation using next token distributions. Now, let's consider a policy, which we'll call pi_theta. Nash MD requires us to generate alternative responses from a regularized policy, which we'll call pi_theta tau. This regularized policy is a geometric mixture of the current policy and a reference policy, which we'll call mu. However, it's not straightforward to generate a sequence from this distribution by sampling one token at a time. This is because pi_theta tau is not a simple mixture, so we can't just choose one policy according to some prior probability and generate a sequence of tokens following that policy. Moreover, defining a normalization constant for the full mixture is computationally challenging due to the large number of possible sequences. Instead, we prefer to generate one token at a time. In our experiments, we generate a token from a marginal mixture, which we'll call pi_theta tau. This is defined in such a way that it depends on the current policy and the reference policy, as well as a normalization constant that depends on the previous tokens. To sample from this marginal geometric mixture over the nth token, we evaluate the corresponding logits of both the current policy and the reference policy, compute their mixture, and sample a next token from the corresponding softmax distribution. We call this the one-step-at-a-time regularized policy. It's important to note that this one-step-at-a-time regularized policy is different from the original regularized policy because the sequence of normalization constants depends on the specific sample path and does not necessarily correspond to the full normalization constant. We'll leave the analysis of the difference between these two policies for future work. Now, let's talk about how we compute the Nash equilibrium using a regularized policy gradient. Our general algorithm involves repeating the following steps. 1. We randomly select a prompt, which we'll call x. 2. We generate two responses, y and y, in an autoregressive fashion in the case of LLMs. The first response, y, is generated by following the current policy that is being optimized. The second response, y, is generated by following an alternative policy, which we'll call pi. 3. We update the parameter theta of the policy in the direction of the gradient of the regularized preference model. The choice of the alternative policy that we use for the second generated sample depends on the specific algorithm we consider. We consider two cases, depending on whether a preference model is learned or not. Section Summary. The section discusses the implementation of the Nash MD algorithm for deep learning architectures in the context of language models, LLMs. It focuses on generating tokens one at a time in an autoregressive manner. The approach involves generating tokens from a marginal geometric mixture distribution, which is different from the original regularized policy distribution. The algorithm for computing the Nash equilibrium of the preference model involves randomly selecting a prompt, generating two responses using different policies, and updating the policy parameters based on the gradient of the regularized preference model. Section: Model-based approach. We'll break down our approach into two categories, model-based and model-free. In the model-based approach, we use a preference model, denoted as P, to determine the preference reward. This model is updated by moving it in the direction of the policy gradient estimate. We also use a technique to reduce variance, which involves subtracting a baseline from the preference. This technique doesn't require learning a value function as a baseline. When the response is a sequence of tokens, we can use a sample-based estimator to the KL based on the sample response. This can be broken down into a sum across token indices of per-token KL estimators. We can then apply a standard policy gradient variance reduction trick. In the model-free approach, the preference model comes directly from human preferences. If humans are immediately available to express their preference between any two responses, we can directly estimate the gradient. This method doesn't require learning a preference model first and is not affected by possible bias from an approximate model. However, it does require having access to human preference immediately after generating the responses. For both approaches, we use an alternative policy to generate the second sample. We'll consider two different algorithms for this, Nash MDPG and Nash EMA-PG. These are inspired by the mirror ascent algorithm and a generalization of fictitious play where we consider an exponential moving average. In Nash MDPG, we define the alternative policy as a geometric mixture between the current policy and a constant, independent of the response. This is inspired by the Nash MD algorithm, which we have proven to be convergent. In the case of sequential generation of tokens, we apply a one-step-at-a-time version of this regularized policy. However, this differs from Nash MD in several ways. It uses a parametric representation of policies instead of a tabular one, and it's not directly implementing a mirror descent algorithm but a simple gradient descent on the regularized preference model. Another difference is that Nash MD uses a KL regularization with respect to the mixture policy, whereas Nash MDPG uses a KL with respect to the reference policy. However, we found that regularizing with respect to the mixture is equivalent to regularizing with respect to the reference policy. We also use an additional parameter to define the mixture that can be further tuned independently. While it's possible to implement Nash MD more faithfully, such as by incorporating two timescale policy gradient versions or exploring variants of regularized policy gradient methods, we believe that the essence of Nash MD is encapsulated in Nash MDPG. This is because the policy gradient algorithm improves the current policy by playing against the geometric mixture while preserving regularization with respect to the mixture. Section Summary. In this section, the authors discuss two approaches for generating alternative policies in the context of preference-based reinforcement learning. The first approach, called Nash MDPG, defines the alternative policy as a geometric mixture between the current policy and a reference policy. The second approach, called Nash EMA-PG, generalizes fictitious play by considering an exponential moving average of policies. Both approaches aim to improve the current policy by playing against the alternative policies while preserving regularization. Section. Consider the alternative policy $pi_theta $beta of Nash MDPG when $beta in 0, 1 takes its extreme possible values, $beta equals $0 or $1. When $beta equals $0, then $pi_theta beta equals O equals pi_theta. Thus the alternative policy is the current policy, and this algorithm is simply a version of self-play, SP, where one improves its policy by playing against oneself. We do not expect this algorithm, even in its tabular form, to enjoy a last iterate convergence to the Nash equilibrium. See the discussion around the OMD algorithm in equation. Now, when $beta equals $1, then the alternative policy is $pi_theta beta equals 1 equals mu $. Thus we are improving the current policy against the fixed reference policy $mu i.e. optimizing $pmapstop_tau pi mu $. Thus this aversion of best response BR against $mu $. This will generally not converge to the Nash equilibrium either because there is no reason that this BR cannot be exploited. Let's delve into the extreme scenarios for the Nash MDPG policy, denoted as pi_theta beta, where beta ranges between 0 and 1. When beta equals 0, the alternative policy becomes the current policy, which is akin to a self-play scenario where the policy improves by playing against itself. However, we don't anticipate this algorithm to converge to the Nash equilibrium, as discussed in the context of the OMD algorithm. On the other hand, when beta equals 1, the alternative policy becomes mu, which means we're improving the current policy against a fixed reference policy, mu. This is similar to optimizing the best response against mu. However, this also doesn't guarantee convergence to the Nash equilibrium, as there's no assurance that this best response can't be exploited. As an alternative to Nash MDPG, we propose another policy, pi, which is a mixture policy defined by an exponential moving average, EMA, of past parameter values. When beta equals 0, the algorithm is simply self-play, and when beta equals 1, the algorithm is a best response against the initial policy. For any other beta value between 0 and 1, the policy uses a mixture of past parameters. However, due to the non-linearity of the policy representation, there's no guarantee that this policy is a mixture of the corresponding past policies. Despite this, previous deep learning research suggests that it could be a reasonable approximation. We then conducted experiments on a summarization task and compared several algorithms for NLHF, including self-play, best response against mu, Nash MDPG, and Nash EMMA-PG, as well as an RLHF baseline. Next, we compared parametric preference models, denoted as P_theta, and reward models, denoted as R_theta. Preference models assign a score between 0 and 1, which can be interpreted as the probability of one generation being preferred over another given a context. This preference is initialized using a language model and trained to fit the underlying human preference probability by minimizing a cross-entropy loss on a dataset. On the other hand, reward models assign a score that can be interpreted as the value of a generation given a context. The reward is defined by prompting the language model and trained to fit the underlying human preference probability via a model. They use the same preference dataset and minimize a cross-entropy loss. In our experiments, we used a summarization dataset built from the TLDR dataset. We trained our preference and reward models on a training set and evaluated them on a test set of high-confidence data. We measured the quality of our models using the expected agreement, also known as accuracy, between our models and human ratings. Our first experiment showed that larger models had better accuracy on the test set. However, the gains were relatively small when going from a 3 billion parameter model to an 11 billion parameter model for this specific summarization task. Therefore, we conducted our subsequent experiments on models with 3 billion parameters only. Our second experiment compared the accuracy of a reward model with a preference model, both with 3 billion parameters. We found that the preference model had slightly better accuracy than the reward model on the test set. Section summary. In extreme cases of the Nash MDPG algorithm, when the parameter beta is either 0 or 1, the alternative policy becomes the current policy or a fixed reference policy, respectively. However, neither of these extreme cases guarantees convergence to the Nash equilibrium. Another alternative algorithm, Nash EMMA-PG, uses a mixture policy based on an exponential moving average of past parameters, which may approximate the mixture of past policies. Experimental results show that larger transformer models tend to achieve higher accuracy in preference modeling, and preference models generally outperform reward models in terms of accuracy. Section. Supervised Fine-Tuned, SFT, Initial Policy. In our research, we start off by using a model called T5XL, which we fine-tune using a dataset from OpenAI. This fine-tuned model is referred to as the Supervised Fine-Tuned, SFT, model, and it's the starting point for all our experiments. We chose the T5XL model over the T5XXL model because it's more efficient and allows us to compare our policies more easily. Our main goal isn't to create the best text summarization model, but rather to test out the new approach we're introducing in this paper, which we call the NLHF approach. We also set up a baseline model, which we call the RLHF baseline. This model is created by starting with the SFT model and then updating it using a method called regularized policy gradient update. We do this update 10,000 times. The reward for this update comes from a model called T5XXL. We also adjust a parameter called tau, and after testing several values, we found that tau equals 0.05 works best. Next, we use the SFT model to initialize two more models, which we call Nash MD and Nash EMMA. These models are updated using algorithms called Nash MDPG and Nash EMMA-PG. The preference model used in these algorithms comes from the T5XXL model. After testing several values for tau, we found that tau equals 0.008 works best for these models. We also tested several values for a parameter called beta, which is used in the definition of the alternative policy. For the Nash MDPG model, we tested beta values ranging from 0 to 1. For the Nash EMMA-PG model, we tested beta values of 0, 0.999, 0.9995, 0.9999, and 1. We then compared all these models to each other. The SFT model was used as the starting point for all models and was also used for the KL regularization. The RLHF model was tested with a regularization coefficient of tau equals 0.05. We also tested a model called SP, self-play, which improves by playing against itself. We also tested several versions of the Nash MDPG model, with beta values ranging from 0.125 to 0.75. We also tested a model called BR, which improves by playing against the fixed SFT policy. Finally, we tested several versions of the Nash EMA-PG model, with beta values of 0.999 and 0.9995. All models were trained for 10,000 steps. The Nash MD and Nash EMA models were trained with a regularization coefficient of tau equals 0.008. We then compared all these models to each other, and the results are given in a table. We'll discuss these results in more detail in the next section, where we'll also talk about how we evaluated our models using a preference model built from a larger model. Section Summary. In our experiments, we initialize our policy with a T5XL model and fine-tune it using supervised learning. This supervised fine-tuned model, called SFT, is used as the initial policy for all our experiments. We opt for the T5XL model for computational efficiency and to compare different approaches fairly. We also establish a RLHF baseline by updating the policy using a regularized policy gradient update with a reward model. Additionally, we use the Nash MDPG and Nash EMA-PG algorithms to update the policy based on a preference model derived from the T5XXL model. We conduct pairwise preference comparisons among all the models, including SFT, RLHF, SP, MD1 to Maryland 6, BR, EMA1, EMA2, EMA1, and EMA. These comparisons are based on 1,000 pairwise comparisons and provide an upper bound on the width of a 95% confidence interval. Section. Evaluation using the PALM2 preference model. We've evaluated our models using the PALM2 preference model, a powerful language model. Ideally, we would have liked to use human preferences for this evaluation, but instead, we've used this model as a stand-in. We've asked the model to choose between two summaries, which we've labeled as Summary 1 foot and Summary 2. This method is similar to one used in previous studies. To measure the preference between the two summaries, we've counted the number of times Summary 1 foot was chosen over Summary 2 feet in a sample of 2,000. This gives us an approximate idea of human preferences. It's important to note that the model we used during training is different from the one we used for evaluation. The training model is smaller and based on the T5XXL model, while the evaluation model is based on the PALM2 large model. Our results are presented in a table, with each entry based on 2,000 samples. We've also provided a confidence interval, which is a measure of the uncertainty of our results. Now, let's discuss the results. Our RLHF baseline model performed very well, beating SFT with a win rate of 99%. This is the highest win rate we've seen against SFT using the PALM2 preference model. On the other hand, the best response against self-play, BR, model didn't perform as well. Even though it was trained to beat self-play, it only scored 94% against self-play in the evaluation. It also didn't perform well against RLHF and other Nash-based models. This suggests that BR might be overfitting to the SFT policy. Self-play, SP, performed well overall, but it didn't do well against RLHF and the Nash MD models when the beta value was less than or equal to 0.5. This suggests that self-play could be a good way to improve the initial model, but it doesn't guarantee a Nash equilibrium. The Nash MD models, especially those with beta values of 0.125, 0.25, and 0.375, performed very well. In fact, the Nash MD model with a beta value of 0.125 was the best performing model overall. The Nash EMA models didn't perform as well as the Nash MD models or RLHF. This suggests that the first-order approximation of the mixture policy might not be the best approach in this context. Interestingly, the Nash MD models performed best when the beta value was between 0 and 1, specifically 0.125, 0.25, and 0.375. This suggests that a model can be improved by playing against a mix of the initial policy and the current policy, rather than just one or the other.